Oh, so since then you guys couldn't hear me at all. Nobody said anything. Okay. So never mind. So the plan right now is, let's just begin. Okay. The plan for today is to discuss. Okay. Uh, discuss problems from last time. Problems from last time. Okay. In fact, rather than me saying the plan and so on, let's just start. Okay. So this is like a warm up. Yeah, because I already said and then I was muted. But let's start. It's better to just start, right? So some warm up questions. Let's see. So in this case here, we have a triangle to begin with. Am I audible now, or am I still not audible? You should have told me earlier. Someone should have told me earlier. Anyways, so yeah, because I was in a different meeting earlier and I had kind of muted myself mechanically. So we have a triangle and we have this point given on BC. A, B, and the midpoint M given. Okay. And we are given the length of the median. Okay. Length of AM is given. That is 2, and the other sides are given. So AM equals to 2, AB equals 3, and AC equals 4. What we want to find is the area. Okay, find the area of ABC. So that is a question mark. So those of you who have tried can tell me. This is just a computational question of the same nature we were doing earlier, is connecting the sides of a triangle with medians and areas, and that whole connection jungle. It's a problem from there, kind of. How would we do this? Okay, from where? Okay. Others have tried. Shana, you and the other person there. So then let me say one thing here. This problem can surely be done. Okay. Calculate, if you just go on calculating things, you can surely do this, because we know the relation, right? We know, so let's write this. We know the length of the median, any median, but let's say AM, in terms of the sides of the triangle. In terms of sides of triangle ABC. Don't we? We know this, right? Last time we did this. So if I call this C, this is not the way we are going to do the problem though. Okay, but I'm just saying that if you want to do this just mindless, just by calculation, you can do this certainly. It's possible to finish this. If these are A, B, and C, then what is the length of AM? We had derived this last time. Even if you don't remember, that is not a problem. I'm not expecting to remember. but just to confirm if this is true. Something like this, right? Anyone? Last time we had derived this was something like this. Maybe there was something more in the denominator. Yeah, yes or no? Yes. Something like this. So this is the thing. So you can certainly apply this formula, right? You can find am square. I mean, you have this relation, right? And you see three of the quantities is given. You can find the fourth one, and so you know all the side lengths, so you can find the area. A very boring way to do the question and to do some calculations, right? So for those who don't know this, this is a homework. Try to. It's just an application of Pythagoras theorem. Try to find the length of the median in terms of the side. It's an important thing to do. Okay, it will help you in a lot of when you later do trigonometry and so on and so on. Consider that good thing. Okay, so this is certainly a way to do it. Do you guys agree? From there you can find the third side because the median is given, and then you can find the area. But we want to do it in a different way. We don't want to find the third side and then do it because only the area is asked. So then how do we do it? So we want to find the area. We want to find the area without finding the third side in that sense. Right? We want to directly get. And if you see the title is parallelograms, right? And that is a technique that we had introduced few classes back, right? Constructing the right kind of parallelogram to complete the symmetry in some sense. Somehow, yes, something, yeah, anything like that. Extending A along what direction? AB or A? Hmm? Okay. So I'll just draw it like so first. AM or DM? Okay, you found BM. Okay. So then, yes, so you can find BM and then you can find the area, but we don't want to do those calculations. Right, we want to see directly we can convert this triangle into some sort of a parallelogram by some cutting, pasting, or some symmetry. We want to see if we can do that. Like Ishana is suggesting something here. We have draw this straight line, but then how are we going to use that? AM is given to be 2. AB is 3. And this is 4. I find this a little strange. Don't go by the picture, okay? The picture definitely does not suggest that. Okay. Uh, but that never mind that. So see, it's also okay to find the area of AMC because area of AMC is going to be half of the area of ABC. It's also okay to find that. But even that seems difficult. I mean, even that seems to be needing MC. So you have to take BC out of the equation and somehow find the area of something. So let me give a hint, maybe, because I'm in fact not able to keep the motivation very clearly. So that's why you guys are not able to proceed. But let me try to give a more explicit. So I'm saying is extend this line so far. So far you have to tell. This whole laptop is a little difficult. Extend it so far so that these are some very fundamental techniques that you use in all every time, many questions. So that this becomes, I want to make a line from C which is parallel to AB. I'm just trying to do that here. Now, both of them as in, yes, yeah, the two parallel lines, it's going to be the transversal certainly, yeah. So how do you relate this with, what's the relation? What is A prime AC? Area of this, how is it related to the area we want to find? It's the same area as ABC, not ABM. So A prime C, yeah, that's what you meant to say, I think, A prime MC, right? Yeah, but this has the same area as ABC. That's good. Now what do we do? So now you know what you should do. You see, I somehow transported that DMC to ABM to this side, right, A prime MC, and now we have this triangle A prime C. Do we know the length of its sides? So maybe Punab, can you say what will be the length of A prime C? If you know. A prime C, what should be the length of this A prime C? Just by basic similarity, right? You have AB, you have A prime C. So it should be the same, right? Because you can see, right, this is equal to this, and just by basic things, right, you can see it's same length, right? And so there's not much to do here, right? It's done because A prime C is 3, M A prime is 2, again, let's see that. And so now you know the side lengths, 4, 4, 4, 3. It's an isosceles triangle. And so now we can just find the area by Heron's formula. We don't have to solve any equations in that sense, right? So this is a strategy in these kind of questions. Okay, here you could have done it either ways, but could have done the calculation, we also got the answer. But this is a very important, very good method. So instead of going to the next warm-up type question, let me actually connect this technique with one of our goals for today, that was proving that things are concurrent. Okay, and I discussed last time about that and so on, but let's get there because we are in the right setting. So I want to exploit this situation so that we can. So then we move to the next question later. We want to move to our goal of showing that 3 lines are concurrent. I'll just write the question. show, this is such a fundamental question, show that the three medians are concurrent. There are several things to learn from the proof of this and so on, which we'll try to do. Several kinds of things we'll learn, actually. This is also a problem I've given. So let's see. Okay, this is expected. You guys would have thought about it for those who were there. So, any ideas as to how you would do such a thing? Showing that three lines pass through the same point. Not even drawing anything because I want to first know what's the idea behind doing this kind. Like a general idea. How do you show the three lines are passing through the same point? Say that again. We thought about this. Like this is the thing. Okay. So the way, see, first of all, let me say this thing that the kind of question this is, you cannot do this problem in a direct way because there is nothing to essentially there's nothing to construct, there's nothing to calculate, there's nothing to return in the end. There is no point you are going to return in the end or anything like that, right? There's no direct constructive proof, at least in the Euclidean world. I mean, you put coordinates and maybe, but we're not interested in coordinates now. Okay, so that's why you cannot prove this directly because you won't arrive. You won't arrive at an object when you end up proving this, right? So the necessarily the way to do this question is to do by contradiction. That is the first step to realize because there can be hundreds of questions about concurrency, but you must realize that this is the approach. Obviously, we prove theorems or concurrency. Now that can be proved. So to show that three medians are passing to the same point, we first take two of the medians. So I'm just going to now elaborate on what Ishana has said basically. So you take two of the medians. Now you want to show that the third median passes through this point only. Okay. So what do? Let's say we so call that call M1. So these two are medians. Okay. Now I want to show that the third median passes through this. So well, one can say, let's say for the sake of contradiction, the third median does not pass through this. I mean, it's absurd, but let's say the third median. Let's say that this is the median, but it doesn't look at all like it. One way is to say that, okay, let's assume that the third median does not pass through. Okay. Then we say, okay, let me see what is the line that passes through the intersection point. What is this line that passes through the intersection point? Okay. And then I will show that the pink line is that line of the same type, is the median. Okay. we show that the pink line is the median. But there can only be one median that you can draw, right, from the vertex. And so it means that the three medians pass the same point, and that other red line which we have drawn, which is not the median, which is the median we said, is actually not the median. Or you can say the same one. Is the idea okay with everyone? Uno, do you get the idea? Nagesh? Okay, nice, good, good. Because this is the thing we are learning here. It's the way when you look at the problem, what kind of proof will work. Like some people seem to be an expert, they just naturally know it, right? They just see, okay, we should do it. So that's the kind of thing we are understanding, these kind of questions. Yeah. So that's the goal. So you take the two of them are the kind of line you're trying to show. The third one, you just make a line, third line, and you show it at the same time. And so then the three lines have to be concurrent because you can only make one line of that type from any vertex. That has to be that, and so they're concurrent. It's almost just irritating, right? Something to that for saying it again and again, right? But to be just rigorous. Okay? So show that the third line is the median. So now we write the what we have here that AM1. You guys think I'm just writing this? Calling this X. So that I'm really surprised. This screenshot was taken at 11. So you want to show that the third one is also the median. And the technique we discussed in the previous question about drawing parallelograms can be useful. So you want to find the ratio AX by XC, AX by XB, right? You want to find the ratio AX by XB. There could be several ways to do this. In fact, for those who are comfortable, like I think Ishana has done this already. If you know if you're comfortable with the way we prove the Ceva's theorem, right? Then you already know the proof because you can find that ratio AX by XB, show that it is 1. I don't, but you're not allowed to quote the theorem. You have to apply the proof here if you can. But there is some simpler method because this is special cases, it's medians. Okay, extending M. Okay, let's do that. So, use electric color. So just making the same thing before. So just try to think, how will this help us to understand AX by XP? That's what we want to understand. Note that A, B, A prime, C is a parallelogram. You can see that. Because you can see that the diagonal bisect each other. See, it's a parallelogram. The full thing is parallel. Try to build on that. Hi Prabhudesh, so a little late. Let me. So this is the second thing that we are doing, but it's kind of connected with the one we did at this. But let me just tell you what we're doing now. Okay? So we are trying to show that the three medians pass to the same point. The plan that we had last time is to try to show that things are concurrent. And the way we are doing this is we said, well, to take a triangle. So concretely speaking, this is what we're trying to do. Take a triangle, draw two medians, as you can see, we have drawn already. So not this two. BM2 and AM1. Draw two medians, AM1 and BM2. So they are medians we know. Now draw a third line. Just draw a third line, the pink line, passing through the intersecting points of the previous two medians. Let's set the X and show that this is also a median. That's what you're trying to do, concretely speaking, right? You draw two medians, BM2 and AM1, they are medians, you know, and you make a third line passing through the intersection, show that that is also median. Basically, we're trying to show that AX is equal to XB. So if you want to ask more questions, you can ask, because this is what we're trying to do. And to that effect, we have drawn a line, and this technique discussed this previously, but either way, you can see that once you do this, it works. Is that you could draw a line, this A prime C that we have drawn extended from C to CA prime, have drawn it parallel to AB. And then you can see that by congruency that BM1 is equal to M1C, so those triangles are actually congruent. AB, M1, and so carefully, A prime, C, M1. They are congruent. And so what we have is a parallelogram. The full thing is a parallelogram. So now, what do you think? Do you think this is the right A prime is the right construction to make? Is it helping us to understand AX, XB? But let's not use that because then you have to prove that, and that's not hard to prove. Okay, so how do you prove? So you are saying that if I call this G, so you are saying that use that AG by GM1 is 2:1. And AG by GM2 is also 2. Yeah, so these two are there, but then firstly, how do you prove it? It's not hard to prove. Okay, so if you can assume that, then can you do the problem? let's assume that. Okay, let's take that statement also, and if we can use that, it's also good. Yeah, that's a very good. So now that is also available to us. Okay. So I'm not saying that GC is to GX is 2:1. I'm not saying that because I don't know if that is the median. But the other two things I know are medians, and so I can write that. So you can use that if you want. But I want someone to notice that drawing the line A prime is not so good. It doesn't help you to understand that ratio too well, right? AX, because that's on the other side, right? I mean, how is X even coming in the picture? At least directly speaking. Ishana, do you see that? This slight problem? Yeah, it's not a, it may still work because it may still do something and it will work, but yes, exactly. If you extend X, then that should work. Okay. So I'm just going to tell this first. Yeah, that's what we should do. Yeah, I was just thinking. So let's extend that, and so let's do one thing. Let's actually remove this thing, otherwise it makes it complicated for us. And then I want someone else to build on it. So if I am extending this, then can someone tell me to what extent should I extend and what should I do? How much should I extend it? Sorry. How much should I extend it? What should I have in mind by doing that? Remember that I want to show that AX is equal to XP. This thing. So to what extent? So what should be the characteristic of this Z? How will I say it is extending, and then where should I stop? How do I prescribe? Yeah, AZ. Absolutely. Right. That's it. That's all, right? You just want AZ to be parallel, simple. And then the rest you can all try to do. Easy from there. That's it. Now you can see your parallelograms once again coming. So let's, yes, this is parallel. That's the, so you have to just do the most natural thing. So use this. I'm not going to complete the proof. The point Z is, we understand. Z. So that construction we're making now, I want you guys to know that it is not a surprising or magic construction, right? We already saw it in a different problem, and we've seen this idea, and they have worked. If you want ratio, then you have to add this in the future. So complete this. So use the construction. We'll not do that now. Simple. I want you guys to try it on your own. Use the construction to show. Please try this. Otherwise, this all will be waste. Show. So again, you can see a parallelogram. Prove that it's a parallelogram. Or maybe it is not completely obvious yet. Let's actually do this now. Sorry. Let's actually do this now. So how is this construction going to help us to show that AX is equal to X? Because we don't, this time the difference is that we don't know if AX and XB are the same, right? We don't know that. Yeah. So maybe I was thinking something wrong. It itself doesn't seem to tell us. Anything is but this is not a parallelogram. We don't know if this is a parallelogram. That's the problem, right? Last time we could say that that thing was a parallelogram because we knew that BM1 and M1C were equal. But this time it's not so obvious that it's a parallelogram. That's the thing. There's more twist to it. And you guys should see that there will be a twist because we are not using BM2 at all. What do we expect? Without using BM2, you don't expect to do the problem, right? What do you expect? We have to use BM2. Otherwise, well, actually, we have not even used BM1. No? Now then, hmm. Sorry. That is also good enough. Good point, right? If you can show that BC and Z are parallel, then it's sorry, equal, then it's also okay. Because then you have pair of opposite sides which are equal and parallel, and so the other pair too will also be equal and parallel. That is a characteristic. But it's not so obvious because we are not using BM2 and EM1 directly. Yeah, like which ones? Yeah. So I already see one similar triangle there, but you can tell me. You should tell me what. Yes, probably I have misled you guys a little bit. This construction doesn't seem to be striking me very useful. So as a hint, because see, we want to use AM1 and PM2, right? So to use AM1, just and you can follow up on this. We'll do it now. Okay. No, no. So that in that problem, there were three lines were already median. I mean, that line AM1 was a median, right? In this case, the CX, we don't know if it's a median. That is the cat. That's what we have all got wrong and missed. So I'm coming up with a. I'm suggesting, not coming up, suggesting a slightly new construction, a slightly because in the spirit that I'm saying this to myself to use AM1 and use BM2. Right? So to use AM1, I'm drawing this line parallel to AM1. See if you can use that. Now you have to use BM2 also. ABC and M2BC. No, 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 no. But ABC is similar to M2BC. No, certainly. Oh, why do you say that is the case? Yeah, right. Because it should not be. Yeah, but so to use AM1, I have drawn this parallel line. Okay. So let's call this our A prime. How can we see anything interesting? So here is a specific question. What can you say about A prime? Can we say it's parallel to BM2? Okay, why? Why is this parallel to BM2? Anyone? Because then we'll be done. Yes. Uh-huh. That's the same thing. If you can show that, how do you show that? That's what we have to basically show. Let's show that Ka prime is parallel to BG. So I've drawn A prime B, which is parallel to AM1. They are parallel. So using that, you have to use that. So BM1, the reason why I've drawn that line is to use the ratio BM1 M1C. This is 1. And so what do we get? We get that A prime G by GC is also 1. Okay, so come on, someone tell me now, why is A prime parallel to, change this a little bit. GM2. Let's say if I say forget everything and just focus on the triangle A prime and C. A prime C. You know that A prime G and GC are equal. Okay, this is very simple. Okay, so A prime C. In that triangle, you have to focus. A prime G is equal to GC. AM2 is equal to M2C. This is equal to this, and this is equal to this. So the two things have to be parallel, right? There is basic similarity. Is that right? No. So you are looking at a triangle. Looking at a triangle here, right? And if I've drawn a line like this, is that let's say this is 3, this is 3, and this is 2, and this is this is 9, and this is 6. Right. So then shouldn't then the lines be parallel? Those two lines. Yes, right. I mean, this is a similarity. Ratios, right? Sorry. Yes, it's a trapezium, right? And it's the reason is that the triangles are similar, right? So if I just place, we just look at a simpler case. So let's say this is X, A, B, C, D, right? So we know this, right? That if this XAB is similar to XAD, then we know that this ratio, right? This XA by XC, the amount by which XAB is magnified to get XCD, right? So XA by XC is the same as XB by XD, right? This we know from similarity, but also the reverse is true, we know. Ratio of pair of sides and a common angle. This is a common angle, right? And this, yeah, this is extreme magnified by a certain amount, but then this is also magnified. XD is also magnified by the same. They're similar triangles. Similar triangles means obviously parallel, because this angle will be equal to this angle. This also is equal to this by similarity. So that's just the Taylor theorem. This theorem, this theorem. So then we are done, right? Then this becomes a parallelogram. And so Ax is equal to x. So please ask any question. Yeah. Anybody has trouble understanding this last similarity point? Say that again. Yes, so in this particular picture, in our main picture, you can consider that we have CM2G, CM2G, this triangle, and then you look at the triangle CAA prime. Right? And so there, these two I'm claiming to be similar, parallel. Yeah. And the answer. And so this easily to get those kind of thing only we draw this parallel lines to project this, to use this ratio BM1, BM1 and M1C on this common line. This idea we have used this several times in the past. We have used this idea. You see, this was a very simple looking question, but the proof is not hard, but also not very straightforward. So all this analysis is good. We understand a lot of things here, but this makes us want a theorem, right? A more easy going way to show that things are concurrent, right? This is pretty, it's already pretty, and this is the easiest, it's supposed to be the easiest, right? Medians are concurrent. If I ask you to show aggregates are concurrent, it will be maybe a little more difficult, I don't know. So we want a more direct machinery. Yeah. So in some sense, we already have that. We expect to formulate it properly. So let's erase this then. Please, if it's not clear, you should ask it. Okay? Ask me here. Let's go back. Let's take some steps back and let's go to a theorem, because now it's the right time to introduce the theorem, right? Because we have already seen that what it takes to prove the theorem. Here is fine. We want to show the third line is also this. That general plan is the same. But how are we doing this? So we are going to use this result called Ceva's theorem, which maybe all of you don't know, but let me just state it. But look at this very carefully. What I'm claiming here is if three lines AD, BE, CF are concurrent. So this will not directly answer our question, okay? This is using that congruence is given, getting some other things, ratios. Okay. Let's state that. If three lines AD, BE, and CF are concurrent, where D is on BC and E belongs to, E is on, we have to get used to these notations now, and F belongs to AB. Okay. If this happens, then it's a beautiful result, extremely strong result, for several reasons. Then maybe I'll just draw a picture. I'm not changing this picture because that's what think about medians more carefully. But this Ceva's theorem is actually a very deep mathematical result. We realize that over time, not now. Any three lines, okay? Then this ratio, product of these ratios, BD by DC, CE by DD, sorry, CE by I should write CE by E. It matters, but for us for now it's fine. And AF. So you see how I'm writing the ratios cyclically. Is equal to 1. So product of these three ratios is equal to 1. If three lines are concurrent. This is not just a matter that given three lines are concurrent, we have a computational result. We do have that, but this is much deeper than that. Okay. So we have discussed this in the past in several different ways. Okay, using a physical reasoning, torques, and so on. Then we tried to do a proof based on our ideas we had in the past, and things like that. There are many more variations of this which I thought about earlier and are there in the theory. So for those who want to review this, you can look at this book. They have a straightforward approach here. Yeah, big approach. Challenges and thrills. Also a recommended book. I think it is section 3.6, concurrency and collinearity. I think by mistake they call it congruency and collinearity. Either way, you can look at this book in this section. Or you can and maybe because our approach to this was very different and that's there in that book and even in other books I have seen. You can look at the videos in this playlist. You literally mentioned Ceva's theorem. Two videos I think will cover it. In the discussing interesting. You can skim through it and try the pause and try the things on your own. That's more important. Okay. That way you will also learn some other things. But this book has a straightforward answer to this theorem. And but it has all the variations at once. So maybe it's confusing. But try to read it if you want. There are other variations like the outside triangle and so on. This is what we have. But now, how would this help us to show that three lines are concurrent? How would it help us to show that the medians are concurrent? That is the challenge. That's the question. Not challenge. That's the question. This seemingly, this question, this result, which seemingly assumes concurrency to prove things, to prove some result about ratios. How can we use this to show concurrency? Is something ubiquitous in geometry and found only in places like geometry. Like converse, using a theorem to prove the converse. There is this thing. Let's just think here simply. How can we use this in our problem? So, but we don't know if GC is the median. Just think, but you're on the right, you got it all. To show that CG or CX is better. Okay. So you guys see what we are trying to show is we're trying to show that the pink line is the median. We want to show that. Does anybody see the difference? If three lines were concurrent, then you get these ratios. But now we're trying to show that the medians are concurrent. But we have kind of reduced the problem to this scenario where three lines are concurrent and we want to show that CX is the median. So AM1, BM2, and CX are concurrent. We have created a concurrency situation. Yes, absolutely. Yes, right. So this exactly the theorem. Now we can use the theorem because we have made the scenario where the three lines are concurrent. Okay, nice. It's done, right? But let's do this. Yeah. So this is D, this is E, this is the one. Just for comparison. I don't need to actually write that. You guys know it, but I'm writing it because. Okay. So use theorem. Use Ceva's theorem because we have three lines that concurrent. Use theorem, and so if we use the theorem, that's right. What does it mean? By using the theorem, Bm1 by m1c, that's 1, right? And m2c by am2. So cyclically going around and writing this ratio. You can do this, okay? Because x is not the median necessarily to begin. But that implies that xa by xb is 1. So we are done. That was very different than what we just did. Very fast. This is a very strange thing that is happening. You may, but don't think that okay, the result is true, then the converse is also true. In this case, now the converse is true. In this case, it is true. But don't take this to be true in mathematics. Obviously, those who have seen more mathematics or seen whatever, you would know that this doesn't always work. But in this case, it's coming out to be true. So we can say that 3 lines. I mean, you can use the same philosophy, right, to show that 3 lines are concurrent if and only if. Now you can use this to show lines. You can just the same thing you can apply to any 3 line situations, right? 3 altitudes or 3 whatever. You could use the same thing. So now it's an even only if result. If you want to show 3 lines are concurrent, just take the ratios base of the ratio of the bases and find its ratio. If it's 1, you can say it's concurrent. I have not proved it kind of, but I kind of proved it for this case. But the proof will be similar, right? Let's actually do that. Let's do it. But yeah, before that, is it so far for the medians case, it's clear to everyone. So now let's move to more general stuff. What do I mean? I'm trying to say that we are going to prove the converse of the result. We are going to say that if the ratio is equal to this, then the 3 lines are concurrent. We've basically done that already, but now we're going to. So what are we trying to do? We're taking 3 lines AD, BE, and CF. We're taking 3 lines AD, BE, and CF, and we know, writing it again, we know that the product of the ratios is 1. We know that BD. So let me just for the moment remove this if and only. This is the Ceva's theorem that we know, but we now want to show the reverse. We kind of already showed that without using the word medians. We know, okay, if this, so if BD by C and C by BA and A by F is 1, then the lines are concurrent. Then AD. This is what we want to do. It's kind of what we did for the medians case. So we are given this condition and we want to show that the lines are concurrent. So we'll just do the same thing. Okay, we will say let there, so let, I mean, just assume that the line that CF is not concurrent. You don't even need to assume that. But yeah, let's say, make it more. Right. Let's say that they are not concurrent. Okay. So say that AD, we're just doing the same thing, you can see. AD and BE, let's say that AD and BE intersect at this point B. And yeah, let's say that AD and BE intersect at the point B. And also say that CX, CF does not pass through. We don't need to write this, but let's make it more pass through. Then, just like we did, right? We want to make a concurrency situation. Okay, be it some other point only. Just like we did for the case of medians, right? That's how we got our result. There's no other way to prove concurrency in that sense. I mean, any other way you see is rather indirect. It has to be somewhere. It has to be like a contradiction. Okay. Yeah. So say let CX be the line passing through P, passing through P. We basically in the end want to show that X and F are same. Right. That's what we want to show, right? And so yeah, so we just do the same thing. Just do the same thing. Now we have created a concurrency situation, right? So by the Ceva's theorem, by the theorem, you will get that AX by XB is same as AF by FB. Okay. Why? Because let's apply the theorem. So if you apply the theorem, then what do we get? We get BD by DC times, just we have created a concurrency situation. But then you already have this equation, and then you have this equation now. Let's combine them. We get AF by FB equals AX by XB. So X and F better be same. Right? Okay. So we just did the same thing like we for medians, right? We kind of showed that CG CX was the median. Okay. But we assumed that it was some arbitrary line, and we found its ratio by using the Ceva theorem. Because if you assume that it's an arbitrary line that passes through that, then you make a concurrency situation. You are able to apply the Ceva theorem. And when you apply it, you get a ratio, but don't get a different ratio. Sure. So we're not going to do anything more today, but just see if this makes sense. Let's just try to go over whatever we did today. I'll give a few problems in the end, but go. So you will see that in geometry, the converse of results is true in most cases. And as you will, there's no such theorem like that, but as you will do more geometry, you will see that. And then you will also be able to look at the result and just say if the converse is true. Like I could give you an idea of how just looking at Ceva's theorem, you could tell that the converse is true. But there's no point in just putting that artificially right now. So over time, you will see, it should imply the converse because of such things. But you don't see that, you see the proof at least. But you will see that most results have converses, and also we will see that most results have what are called duals. If you take a statement and you replace the points by lines and lines by points, you get another statement that will also be true. Menelau's theorem is an example. Okay. So geometry has some very interesting. Geometry is more than just what we are writing. If we are doing geometry by writing these letters, but geometry itself is more. And so we get some surprising things. So now, if it is clear, if it's not, then ask me. If it's clear, then so you see we have spread out the Shiva's theorem over several classes, so that we step by step will do it. Now we have the full thing. So now if you want to show concurrence, we supply the result. But before I give you the problem, you will see that now we basically know that this thing implies concurrence. Okay. So what this will help us is obviously it will help you to show that many things are concurrent. Good, that's fine. But it will also help you to uncover some very deep facts about, strange facts about concurrence. Because see, these three are these six numbers you see on there, three numbers, six numbers that you see, the product is 1. But then if you kind of cyclically permute them, you kind of switch the numerators and denominators of each of them, then also geometrically you get some very different lines, right? But algebraically, since the product is will remain 1, those three will still be concurrent. Surprising results will come. Yeah, if you just switch the numerators and denominators, you will still get a concurrent thing, right? You will still get the same ratio as 1, product is 1. But geometrically, something very strange will happen. But this algebraic condition will tell you that they will also be concurrent, which may not be very obvious by just looking at geometry. Okay, and then they can do many more things like this. So you see, this will be a very, so this will, what I'm trying to say is that this will give you surprising results about concurrency. Okay. Or rather, it will help you to understand the nature of concurrency. Concurrency is preserved under many things. This will help you to kind of show them vigorously, or even show them. That is the point. That's the nature of algebraic condition, because algebraically could see things in a could apply more things. Geometrically are not so easy to understand. A challenge would be maybe then to understand them geometrically. Right. So obviously there are obvious exercises to show that I'm not even writing. I just show that the medians are concurrent, the medians are additives are concurrent, and you should just do this. This should be excited to do this, right? Diagonal bisectors and so on, using this to try to show that they are concurrent. Now, let me give you some interesting question. It's a little challenging. Yeah, this is just 2 minutes, okay? We'll just end. It's over time, but this. So, how do I want to say this? So, what I'm going to say is, if you reflect these medians, this is a challenging question. If you reflect these medians about, reflect the medians Now these are the angle bisectors. Okay, so these are the angle bisectors. So that's what I said. Just think about this. I'm not expecting that you will directly do it, but you can angle bisectors. So angle bisectors are congruent. I'm assuming here that's the homework you should do. Sure. But assume that all that. Then what I'm asking is, if you if you reflect the medians about the angle bisectors, okay, so you understand the angle bisector is a line and you reflect the median, so because this one will come somewhere here, right? And this BE, when you reflect, will come somewhere here, and similarly the other median are even drawn, but if you reflect, show that they are also concurrent. Maybe it's a little too challenging, but just try it. Let me, I thought of an easier one, which is actually easier, is the following. Just think about this one. Okay. Because this is actually something, all the three are actually special. But this is just a challenge problem. Okay, it's not something that I'm expecting you to be able to do. This one is like this. You take the three altitudes. You guys can now show that they are concurrent. Just to calculate the length of the bases also. Pieces. So show not that we have theorem. But I'm saying that if you take this now, if you reflect the altitudes about the angle bisectors, this is easier. I'm not going to draw all the angle bisectors, it will become a mess. So I'll just draw one of them. So you take this altitude and you reflect this about the angle bisector, so you come somewhere here. Reflecting it. Just compute the angles, you'll see something special happening. These blue lines will be special. Okay. So I'm reflecting, so that means this angle is, and do the same for the other. At least try to draw it and see what you get. Something very interesting. Okay. Then those three blue lines will also be concurrent, and that is actually going to be the circumcenter of the triangle. Center of the circle. That is the angle bisector. Okay. The blue one is a reflection of the angle bisector, a reflection of the altitude about the angle bisector. Okay, that's why you see I've drawn these angles are equal, the small angles are equal. Okay, so you see, so I've taken this AX, this is the altitude, AD is the angle bisector, and I've reflected AX about AD. Okay, and do this reflection for all the three altitudes about all the three angle bisectors, corresponding ones. Then those three lines will also be concurrent, but in fact, I'm telling you, hint in some sense makes the problem easier, is that they will meet at the circumcenter. So that is something to take. This will again become a very simple problem by using some symmetries of this product, but we'll see that later. So the other problems which I had given, I'll not discuss that today. You guys try them. I'll send it to the others who are not sent. And we'll also discuss them next time, and we'll do a few results like this. Okay, then. Any questions then? So then we'll stop.